Howdy, howdy. Okay, in this video, I'm going to start talking about electron configuration. This might be 2 videos, or it might be 1. I'm not sure yet, so bear with me. First off, electron configuration is incredibly confusing. Okay? You are going to be confused. That's okay. About the time I start going through the periodic table is when you're going to start really going, oh, that's what's going on. Okay? So don't freak out if you're confused when I'm starting. I'm going to start off by giving you some disparate information that may not necessarily seem like it goes together, but it will all come together at about the middle or end of this video, depending on when I stop it. So, that said, let's get started. I need to add some stuff to the board I forgot, and then we'll get going. Okay, now I'm going to try and color code this as I go, so bear with me as I'm probably frequently switching between colors. First off, the very first thing you have to understand if you're going to get electron configuration, you have to understand this. When we did Bohr diagrams, I lied to you. Okay? I did that because Bohr diagrams are a simplified version of what we are going to talk about today. They are the physical science version, but I had to refresh you on that before we got into this, because this won't make any sense if you don't know how to do Bohr diagrams. So, first basic premise, every energy level, which when we did Bohr diagrams, there were up to 7. Those are the circles around the nucleus, okay, where the electrons are found. Every energy level adds 1 new subshell. So energy level 1 is composed of only 1 subshell. Energy level 2 has 2 subshells. Energy level 3 has 3 subshells. 4 has 4. 5 has 5. 6 has 6. That's 2 fingers. Let's try that. 6. Okay? The higher you go, the more energy levels you have. That said, let's go ahead and get started. At this point, we might as well just dive in. The first subshell is the S subshell. And all of these are lowercase letters. If you write them uppercase, if you capitalize them, they are wrong. Now, considering Bohr diagrams, pause this for a second, and considering our Bohr diagram, how many electrons should the S subshell have, considering that the only subshell in the first energy level is the S subshell? If you got 2, that is correct. Okay, the first energy level holds 2 electrons because the S subshell only holds 2 electrons. So there are 2 electrons in the first energy level. That is just the S subshell. I wrote an S instead of a 2. Okay, the first energy level that has an S subshell is energy level 1. That one should be obvious. The first period on the periodic table that has an S subshell is also period 1. At this point, it's fairly simple. Now, this last one, there's not really any good way for you to predict it, so I'm just going to tell you that the largest known shorthand for the S subshell is 7s2. Now, typing this out, if you don't feel like going in to do a superscript or you don't know how, I will tell you that you can also write 7s caret 2. This caret is shift 6, and that will put a caret up. Okay, and so that will tell me that you know that 2 is supposed to be an exponent. Okay, the second subshell is the P subshell. The P subshell, considering that energy level 2, and these are the actual number of electrons that the energy levels can hold, as opposed to the lies that I told you in Unit 1. The actual number of electrons that energy level 2 can hold is 8. Now, considering that the second energy level has both the S subshell and the P subshell, and S holds 2, how many electrons, then, should the P subshell hold? Well, The p subshell, if the s is accounting for 2 of the 8, and the p has to pick up the rest, this has to be 6. So the p subshell can hold up to 6 electrons. Any more than that, it ends up somewhere else. But it can hold up to 6. Okay? The first energy level that has a p subshell is energy level 2. And it first shows up on the periodic table on period 2. Largest shorthand is going to be 7p6. And so that would be 7p caret 6. And that's the last one I'm going to write out like that. At this point, you either get it or you don't on this end. You're doing this. Okay, now energy level 3 introduces the D subshell. Now, once again, I'm going to tell you that the third energy level has an actual cap of 18 electrons. 2 of those are S. 6 of those are P. And so all the rest have to be the D subshell. Well, that means D has to be 10. So D can hold 10 electrons. It first shows up on the third energy level, but it does not show up on the periodic table until period 4. Largest known shorthand is going to be 6D10. And that leaves us with one final known, the F subshell, which is the largest subshell that we have actually confirmed its existence. We have actually found elements that hold this subshell, the F subshell. And I want you to tell me, I'm saying this as if you're actually sitting in the room, I want you to figure out how many electrons the F subshell can hold, considering the same information. The fourth energy level can hold up to 32 electrons, and 18 of them are already accounted for in the S, P, and D subshells. That means that the F subshell has to have 14. The F subshell holds 14 electrons. First shows up on energy level 4, but the F subshell does not show up on the periodic table until period 6. And its largest known shorthand is going to be 5F14. Now, I'm going to point out some patterns here, which a couple of you might have noticed. I had 1 or 2 people who caught this in class. What's the difference between 2 and 6? Well, it's plus 4. What's the difference between 6 and 10? Well, it's plus 4 again. Plus 4. So if we wanted to figure out how many electrons were here, we would add 4. And so our fifth subshell should have 18 electrons. Our sixth should have 22. Our seventh should have 26. And our eighth can hold up to 30 electrons. It's just 4 more every time, so far. Now, we could discover our fifth subshell tomorrow, and it could be 5 more. But the pattern holds so far that we are gaining 4 electrons every time we introduce a new subshell. Now, these have not been named because we don't know anything about their shape. If you're wondering where S, P, D, and F come from, they stand for big words. S is spherical. I believe P is, it's para something. I don't know exactly what it is. And D and F, I've never known what D and F stand for. But they stand for words that refer to the shape of that energy level. And they all have different shapes. And let me tell you, they get weird. Okay, I'm not going to quiz you over any of that. You just need to know that S is 1, P is 2, D is 3, and F is 4. And that's it for this screen. So, oh no, there's one more thing I want to do before I change this up. I want to show you what these actually stand for. Now, some of this you should have already figured out, but I want to go ahead and walk through it anyway. So let's take 7s2. Okay, this is the shorthand electron configuration for radium. Okay, and you can tell that based on some information that I'll give you at the end of this video. First off, the S. That tells you which subshell you're talking about. So this is the S subshell. The 2 tells you the number of electrons in the subshell. So according to 7s2, radium has 2 electrons in the S subshell. So its S subshell is full because it can only hold 2. And the 7 is the energy level. Okay, so radium has 7 energy levels, 7 full circles on its Bohr diagram. In the outermost, it has 2 S electrons. That's what this tells us. Every element has a unique shorthand electron configuration that we can use to identify it. Okay, and we'll get more into that later. They also have longhand electron configurations, but those are kind of long and messy, and I save those for at the end after you kind of understand what's going on. So, now I'm going to erase all this. So if you did not get anything down, I'm going to step off screen. I want you to pause the video, make sure you have all of this down. You might want to take a picture of, I'm pointing the wrong way. There we go. Of this, and insert it into your notes document. Okay? Highly recommended. Or you can rewrite it on paper and add that. But I would, either way, I would definitely recommend getting this into your notes because this is super helpful. So I'm going to step off screen and I'm going to pause this. Okay. We're not going to do a Bohr diagram yet. I am going to draw out a little graph for you. That is a very useful visual aid, but it is most useful when applied over something else. In fact, I'm going to erase this and move it over so that it's in the margin over here so that it won't be in the way when I change the page here in a second. So let's do this over here instead. Okay, the farther up this graph we go, the higher the energy requirement for electrons. Okay, so this is how much energy the electron has to have in order to stay in that location. So our first subshell that we are going to fill is energy level 1, which is what these are. It's energy level 1, 2, 3, 4, 5, 6, 7. The first energy level we're going to fill is energy level 1. And energy level 1 has only one subshell. It's the S subshell. So this is the 1s subshell. It is the lowest energy subshell of any of the subshells in any energy level. It will always fill first. After the 1s subshell is full, energy level 1 is full. And so we go on then to energy level 2. Well, energy level 2 also has an S subshell, which is going to fill first. But then after the 2s subshell fills, the 2p subshell is going to fill. which has just a slightly higher energy requirement, which means that the 2s subshell has to be filled first. Now that takes us to the third energy level. Third energy level, same. It's got an S subshell, then a P subshell. And then, obviously, since this is the third energy level, it has to have the D subshell above that. But there's a problem that we run into with the D subshell, and this is the first case of this happening. As your energy levels get larger and larger and larger and encompass more and more subshells, those subshells start to overlap. So here's the issue. The 4s subshell is lower energy than the 3d subshell. So because of that, the 4s subshell fills first, before the 3d does. After 4s fills, then 3d fills, and then after 3d, we get 4p. And this pattern continues, annoyingly so. After 4p comes 5s, then comes 4d, then 5p, then 6s. And at this point, we get to go all the way back to to energy level 4, because this is where our F subshell first shows up. And I drew that too low. I'm going to raise that a little bit. After that F subshell, we go back to D. So our 5D subshell fills. Then our 6p subshell fills. Then our 7s subshell fills. Then we backtrack again to 5f. So our 5f subshell fills, and then the same pattern takes place again. After 5f comes 6d. After 6d comes 7p. Now, logic would dictate that the next subshell should be 8s, but we have not found an element yet, or rather, we haven't confirmed an element yet, that exists with that many subshells. So this is all known subshells at this time. Now, I'm going to pause this real quick. I would again encourage you to take a picture. I know this is in a kind of a crappy spot. If you ask someone in the class, they might be willing to send you a better version of this picture since I did it all in the light during class. But I'm going to put up a periodic table behind me so that you can see that. And I would encourage you to get out your periodic table if you can, or pull it up on your phone so that you can see it and this video at the same time, in case the one I'm putting up on the board is a little hard to read. So I'm going to pause this, and I will be momentarily back with the periodic table in the background. I just realized that I have an opportunity by putting this on the board that I did not have with my class, with my kids in actual class. So you'll actually get a bit of an advantage here that they did not. First off, I need to explain the blocks. So the periodic table can be divided up into 4 different blocks, one for each subshell. The S block, the P block, the D block, and the F block. Now, with a little logic, it's not that hard to figure out which one's which. The S block is 2 elements wide, the P block is 6 elements wide, the D block is 10 elements wide, and the F block is 14 elements wide. So I'm going to outline these in their respective colors, and this is the thing I couldn't do in class. And hopefully this will help as a visual as we're moving forward. So, Well, I'm sure that's really annoying in the video. This is our S block. It's 2 elements wide and 7 elements tall. And I'm going to go ahead and write in He here, because helium is part of our first energy level. So it only has one energy level. It only has one subshell. It's part of the S block. It is not part of the P block. Now I'm going to have to erase some of my table here, but it's the part that is the easiest to understand, so hopefully that won't be a huge loss. Okay, so this is our P block. Then the D block is all of the transition metals. Watch my hand wobble as I draw long, not straight lines. And then the bottom is the F block, asterisk. So the F block is these elements, the lanthanides and the actinides. But 2 of the elements down here are not lanthanides or actinides. They are transition metals. So lutetium and lawrencium are not part of the F block. There. So hopefully this should be helpful as we move forward. Now, notice again, the S block, which can hold 2 electrons, is 2 elements wide. The P block, which can hold 6 electrons, is 6 elements wide. The D is 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F is 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And these 2 are here, part of the transition metals, part of the D block. Now, looking at this, and bearing in mind that I had to erase energy level 1, we have here, and I'm going to mark out the helium. Remember that that goes there. This is the 1s subshell, hydrogen and helium. Okay, after the energy level 1, we get to energy level 2, another S. So this is the 2s subshell. Then we come to the 2p subshell. Remember, energy level 2 is the first energy level that has a p subshell. So there is no 1p. It's just straight to 2p. There is no 1 or 2d. It's straight to 3d. And ditto for F, no 1, 2, 3. It starts at 4. So this row represents our 2p subshell. Then we come back over here. Well, first here. Next is 3s. Then 3p. And logically, next should be D, but we see that the next on the periodic table is actually 4s. Then comes 3D here. Now, here's the first spot that you have to pay attention to, because this is an easy mistake to make. This is the 4th period of the periodic table. It is not 4D. It is 3D. Okay? The way you have to remember that, D is the 3rd subshell. It shows up in the 3rd energy level. If you remember that, you know everything you need to know to identify your D subshell. D starts on 3, so this has to be 3D. After 3D comes 4P. then 5s, this is 3, so this has to be 4d, then 5p, and we're still going in the order of this. As we work our way up, we're bouncing back and forth across this. We're going in order on the periodic table. So after 5p, we're right here. Next, according to this, is 6s. Well, 5p, next in the row, is going to be 6s. Now, after 6s, we go all the way back to 4 for our first F subshell. And remember, this is where the F block goes. It goes between this spot here and this spot here. So we go from here down here. So this top row, the lanthanides, are all the 4F subshell. Again, remember, you have to remember, F starts on energy level 4. Even though it's in period 6, it starts on energy level 4. So this is 4F, not 6F. Then after that, we head back up where we left off with 5D, then 6P, 7S, 5F, 6D, and last but not least, 7P. Okay, this is where our shorthand starts to come in. Now, this gives us the first two parts of our electron configuration for the shorthand. Okay, zirconium is in the 4D section, so its first two characters are going to be 4D. To get the exponent, we count how many columns over it is in its own block. So this is column 1, this is column 2, it's in column 2, so its exponent is 2. 4D2 represents zirconium. Meanwhile, over here, pointing in the wrong spot, aluminum is 3P, so it's going to be 3P, and it's the first column, it's in the first column, so its exponent is going to be 1. How about uranium? I want you to take a crack at uranium. What's uranium going to be? Pause this and write it down. Uranium is in 5F, so it's going to be 5F with exponent 1, 2, 3. I wrote a 2 for some reason. 1, 2, 3, 4. What's helium? I hope you said 1s2 because it technically goes right here. This is where we stopped the first day in class, and this is where I'm going to pause here. I will switch back, or I will start another, post a second video. Good Lord, I can't talk. I will post a second video going through longhand electron configuration, and that should help nail this down a little bit better. So, hope this helps. I'll see you in the next video.